This first method for integrating is called integration by parts. It is useful when you have an integral of a product, and sometimes the product may be a constant. You'll see an example like that. So typically you have a product, and often, not always, but almost always, one of the terms is going to be a function that if you keep taking its derivative, it'll eventually go to zero. So essentially a polynomial. Let's look at how to apply it. The general process is you've got a product, you're going to call one of the functions u and the rest of the integrand dv, and then you're going to get du and you're going to get v from those two variable names. And the integral of u dv, which is the integral you want to evaluate, is equal to uv minus the integral of v du. So that's what this says, but let's see how to actually apply this. In the first example here, we want the integral of x sine of x dx. So I look at this and I see I have a product. I have an x term times a sine x dx term. So I notice that x, if I take its derivative, it'll be 1, and if I take the derivative again, it'll be 0. So I'm going to let u be x, and I'm going to let dv be everything else. Now, I said I need du, so since u is x, du must be dx. And v is obtained by integrating dv, so the integral of sine of x dx is going to be negative cosine of x. When doing these, there's no need to bring a constant c into it. That'll come at the very end. So now I've got my u, my v, my du, my dv, and I'm ready to actually apply integration by parts. So it says the integral of x sine of x dx is equal to u times v. So that's going to be negative x cosine of x minus the integral of v du. V is negative cosine x. I'm going to bring that negative sign out. I've got cosine of x, and du is dx. So finally, I can evaluate that remaining integral on the right-hand side. I have negative x cosine of x plus, and when I integrate cosine of x, I get sine of x plus c. And it's at this point you bring the c into your answer. And that's it. Let's take a look at number 2, our second example here. Now this one, it's not apparent what our two functions are, but you could think of natural log of x as 1 and 1 dx as the other term. But when you have a natural log of x in your integral, this is one of those rare exceptions where instead of letting u be the term whose derivative goes to 0, you let u be your natural log of x. And that means that dv is going to be the 1 dx term. So du is the derivative of the natural log of x, which is 1 over x dx. And v is the integral of dx, which is just x. So now when we integrate, u times v gives us x times the natural log of x minus the integral of v du notice that our integrand here is 1, so it simplifies very nicely, which leaves us with x log x minus the integral of 1 dx, which is x, plus our constant c. And that would be our answer here. Then you've got another term with a polynomial, which is in example 3. This is the integral of t squared e to the t dt. So I see the t squared is my polynomial. I'm going to let u be t squared. And again, dv is everything else, so that's going to be the e to the t dt, which means that du is 2t dt, and v is e to the t, because the integral of e to the t dt is itself e to the t. This is going to give us uv, so we've got t squared e to the t minus the integral of v du, so that's going to be 2t e to the t dt. And now this integral that remains requires another round of integration by parts. So I'm going to say u equals t in this case, dv equals e to the t dt. Now we have du is dt, and v is still e to the t, which brings us to, we have t squared e to the t remaining from our first round of integration, minus 2. And now, just to make sure I don't make a mistake with distributing, I'm going to do the integration by parts inside brackets here. So uv is going to be t e to the t minus the integral of v du, which is e to the t dt. And that means we have t squared e to the t minus 2t e to the t. The minus 2 distributed with the negative is going to give us plus 2, and the integral of e to the t is e to the t plus some constant c. And there's our answer there. Now, there is an alternative approach that you may like. It uses integration by parts, but it tends to be referred to as the tabular method. And the way that it works is you tend to define your u part and your dv parts. U is going to be t squared. Its derivative is going to be 2t, and then 2, and then 0. dv is going to be e to the t, and the integral of that is still e to the t. The integral of that is still e to the t, and its integral is still e to the t. And then I'm going to look at the product of the diagonals. The first product, I'm going to multiply by a plus sign. The second product, I negate. The third product, I add. And if there were more, it would continue alternating signs, but it always starts with the positive. And so this means that our answer is going to be t squared e to the t minus, this is the second product now, 2t e to the t plus, now I'm on my third product, which is 2e to the t. And because this was an indefinite integral without any values, I'm going to add a constant in there. And notice that this answer is exactly the same as what we got when we did the hardcore version of integration by parts. So this is very useful when you have a polynomial term whose derivative eventually goes to 0. It's might be a little bit more confusing if you're doing it for, let's say, problem 2 that we just did. But it's a nice shortcut approach. Let's continue to problem 4 here. So in 4, we've got the integral of the arctan of x. And this is another one where it looks like you don't have a product, but you could view arctan times a 1 dx. And so there is secretly a product hidden in there. And this is another one of those exceptions where instead of letting u be the 1 dx, I'm going to let u be the arctan function. And what cues me in on that is that I know that u is going to give me du. And I know the derivative of arctan. I don't know the integral of arctan. So it would stump me if I let dv be arctan dx. So for that reason, again, I'm going to say u is the arctan of x. dv is going to be the 1 dx, which means that v is x. And du is going to be 1 over 1 plus x squared dx. So now we start putting these together. And according to integration by parts formula, u times v gives us x times arctan of x minus the integral of v du, which is x over 1 plus x squared dx. And I look at this remaining integral, and I realize I could use u substitution here. And I recognize that because the denominator has a quadratic. The derivative of a quadratic is going to give me a line, which is what I have in the numerator. So I am going to let u equal 1 plus x squared, which means du equals 2x dx. Which, when I apply this now, we have x arctan of x minus the integral 1 plus x squared, I just said is u. X is, or x dx is going to be 1/2 du. And I got that from this line here. Divide by 2 in order to get x dx, and we've got 1/2 du. And so if I continue with this, I have x times arctan of x minus, I'm going to pull that 1/2 out, and when I integrate 1 over u du, I get the natural log of u, but u is 1 plus x squared plus c. And there's one more example problem left. And this is the integral of e to the x times sine of x dx. The trick I'm about to show you is applied whenever you have an exponential times a sine or a cosine function. And hopefully as we go through this, you'll see why it's useful in this type of scenario. So let's just start through this. I see I have a product here. I have an exponential times a trig. So I'm going to let u be one of them. In this case, since neither of them ever has a derivative that goes to 0, it actually doesn't matter which one I let u be. What's important that is that whichever I let u be in my first round, it has to remain the same in the second round. And you'll see what I mean because we're going to have to do integration by parts twice. So let's let u be e to x, which means dv is sine of x dx. du is e to the x dx. And v is negative cosine of x. So after one round of integration by parts, this is going to give us u times v is negative e to the x cosine of x minus the integral of v du, which is going to be negative e to the x. I'm going to bring the negative sign out to get plus e to the x cosine of x dx. So now again, this remaining integral on the right hand side is an exponential times a trig. So I'm going to use I'm going to use integration by parts for a second round. So I'm going to let u be e to the x because u was the exponential in my first round. dv now I'm going to have as cosine of x dx. du is e to the x dx. And v is sine of x. So I'm going to rewrite this starred line here. We have the integral that we want to find is the integral of e to the x sine of x. We know that's equal to negative e to the x cosine of x plus, and now according to integration by parts, this integral is u times v, so that's going to be e to the x sine of x minus the integral of v du, which is e to the x sine of x dx. Now at this point, it may seem like a lost cause because it doesn't appear that we're ever going to get rid of an integral of an exponential times a trig. But notice that the integral on the left we also have on the right. They're exactly the same. I am going to add the integral on the right to the left-hand side. Right, so I'm going to add integral e to x sine of x on the right, and what I do on the right, I also have to do on the left. And that's going to give me 2 of these integrals. But on the right-hand side, we have negative etx. Actually, I'll just make it etx times, I'm going to factor out that etx, and we have sine of x minus cosine of x. And the integral we just brought over to the left side. Now that integral is what we want to find, so I'm going to solve for that by dividing by 2. And that gives us the integral of etx sine of x dx is 1/2 etx, or etx over 2, times sine of x minus cosine of x. And this factoring isn't necessary, I just think it makes it a little neater, plus c and there's our final answer.